Hello students, viewers, and subscribers. There is another problem which is originally problem 9.5 solved by classical methods such as the three moment equations. There, the problem is solved in more detail than 10.5 by the slope deflection equations, where we just verify the moments at C and D. Then 10.5 A, then 11.5A by the moment distribution method, where we also verify the moments at C and D. And this time 11.5B by the matrix approach. So this is the matrix approach. So we have support settlements. E is 200 gigapascals and moment of inertia is 500 times 10 to the 6 mm to the 4th. So it's constant, and that would be 100,000 kilonewton meter square. So determine all support reactions by matrix approach this time. So let's verify the support reactions. So we have support settlements B12, C 8 mm, D 14 mm, then at E 6 mm. And the moment of inertia of portion ABC is 1.2 of I, portion CDI and DEF 1.5 I. So because this is matrix approach, then there are four unknowns here, namely theta B, theta C, theta D, and theta E as the four unknowns, so that we can use your portable calculator in solving for the important things, so that we can analyze this problem. So since we only analyze B, C, D, the rotational displacements, then the moment due to 15 kilonewton load is not, we do not consider this as fixed, because we only consider B, C, D, and E. So the moment resistance is 15 times 2, so we have 30 here. Then for portion BC, we have to consider the side sway moment as well as the load. So fixed moment BC is due to the load. The formula is moment B over L square, quantity 2L minus 3B. The moment is treated negative because it is counterclockwise, and remember that these fixed moment formulas are based on slope deflection equations in which clockwise rotation positive. So that's why it's negative 120. B is distance of the load from C, which is 2 over L square, which is 5 square. Quantity 2L, so 2 times 5 minus 3 times B. Then for the support settlements, the rotation of BC is counterclockwise, and delta is the difference of these support movements, 12 minus 8, 4 mm, and 4 mm is treated negative in the formula. Side sway moment formula is negative 6EI delta over L square, where delta for counterclockwise rotation is treated negative. So negative 6EI is 120,000 because EI is 100,000. Then because I here is 1.2, so 100,000 times 1.2 is 120,000 kilonewton meter square. Then delta is 4 mm and it is treated negative. So it is negative 38.4, this one. Then the value here is positive 115.2 combining. So fixed moment BC is 76.8 kilonewton meter, and it is positive. That's why it is clockwise application here. Fixed moment CB is due to the load, negative 120. A is 3 over 5 squared 2L minus 3 times A. So negative 120 times 3 over 5 squared, quantity 2 times 5 minus 3 times 3, then plus sideway moment 115.2, which is the same. So it is equal to 100.8 kilonewton meter. Then for CD, fixed moment CD, due to the load, WL square over 30, then sideway moment negative 6EI delta over L square. Delta this time is 14 minus 8, which is 6 mm, and it is 0.006 meter treated positive. So fixed moment CD negative 24 W, negative moment at the left, L square, so 6 square, all over 30, negative 24 6 square over 30, then due to support movements or sideway, negative 6 EI, 100,000 this time because this is just I. Delta is, as I said, the rotation of chord CD is clockwise, so 6 mm positive 0.006 over 6 square. Value, negative 28.8, this one, negative 100. So combining negative 128.8, and since it is negative, so it is also it is counterclockwise here. By the way, 100.8 is clockwise CB. Fixed moment DC is due to the load positive here at the right, so WL square over 20, then minus 100, which does not change for sideway moment. That would be negative 56.8, so it is counterclockwise as shown, 56.8. Then fixed moment DE is equal to negative WL square over 12, negative 24 4 square over 12. Then sideway moment is negative 6EI delta over L square. Delta this time is treated negative, 14 minus 6 is 8 mm because the rotation of core DE is counterclockwise. So negative 6, EI is 150,000 because I is 1.5 of I here. Then negative 0.008 over 4 square. That would be negative 32. This one is 450. 450 minus 32 is positive 418, and it should be clockwise as shown. Then finally, fixed moment ED is positive 32 because we have symmetrical loading for DE. So the fixed moment due to the load at the right is positive, then plus 450, so 482, and it is also clockwise as shown. Then for cantilever portion EF, this moment, which is the overhanging moment, not by treating EF as fixed because we only consider BCD, is 24 times 1 moment arm 0.5, so that's why we have 12 there, and it is so negative, moment EF is negative, so that's why it is counterclockwise. So therefore, the net nodal load at B is 30 clockwise plus 76.8 clockwise. Therefore, because these are fixed end moments, the load is opposite to the fixed end forces, fixed end moments. So it should be counterclockwise. So 30 plus 30 clockwise plus 76.8 clockwise is 106.8, and it should be counterclockwise, opposite to the net moment there. So 106.8. Here we have 100.8 minus 128.8, that's negative 28. Negative 28 is clockwise because the positive moment in the universal sign convention is counterclockwise positive, or in softwares, in matrix, counterclockwise positive. So 28 clockwise at C. At D, this is counterclockwise counterclockwise, this is clockwise. So 418 minus 56.8, whatever is the result. So clockwise is treated positive, then counterclockwise negative, whatever is the result, that's the value. If it is positive, it's positive because we oppose the net fix and the net fix and moment at the support at this node D here. So it is 361.2. Again, 418 minus 56.8 is positive 361.2. So that's why it is counterclockwise here. Next is 482 clockwise minus 12 counterclockwise is 470, and 470 is positive. The net moment is clockwise 470, so the load is opposite to that 470 counterclockwise, and that is positive. So for the numbering, this is 4, 6, 8, 10, U4, U6, U8, U10, and these are the global or nodal loads, net nodal loads. Then we have to prepare the stiffness of, because we also need the displacements at A, so we need to prepare everything. Stiffness of AB, 12 EI, which is 1.2. So 12 times 1.2 divided by L cube, 2 cube. So 12 times 1.2 divided by 2 cube is equal to 1.8. So 1.86 times 1.2 over 2 square is 1.8 also. Then the negative of that value, and I will not explain the preparation of this stiffnesses of members because as matrix structural analysis students, you should know that. For BC, it's the same, 12 times 1.2, we factor out EI, all over 5 cube, so this would be the values 3, 4, 5, 6 for BC. For CD, 12 times 1, because I is 1, EI is 1, over 6 cube, so this would be the values. For DE, 12 times 1.5, all over 4 cube, so this would be the value for this cell. Then 6 times 1.5 over 4 squared, then the negative of that, then you just copy, and you should know the rest. This is 4 times 1.5 over 4, so that's why it's 1.5, and this is half of 1.5.75, the negative of the first row. Then copy that second row, except that we interchange position 1.5 and 0.75. Anyway, you should know that. Then for EF, that's the stiffness and the numbering. So since we are interested only of the displacements at numbers 4, 6, 8, 10, and these are the loads, so these are the loads, then equals EI, then we have 4, 6, 8, 10, U4, U6, U8, U10. So for 4, 4, only consider BC, CD, and DE. So BC, 4, 4, we have 0.96 here, and it's only 0.96, so that's why we have 0.96 there. 4, 8, 4, 6 rather, so 4, 6 is 0.48, so we have 0.48 here. 4, 8 non-zero, 4, 10 non-zero, so that's why by symmetry we copy 0.48 here and 0, 0. Then we have 6, 6. 6, 6 is 0.96 here plus 2/3. 0.96 plus 2/3 is 122 over 75. Then 6, 8, row 6, column 8 is, we have 1/3. So that's why we have 1/3 here. 6, 10 is none, so that's why we have 0. Then copy 1/3 and 0 here by symmetry. Then 8, 8, 8, 8. We have 2/3 here plus 1.5. 2/3 plus 1.5 is 13/6. Then 8, 10. 8, 10 is 0.75. So that's why we have 0.75. Copy 0.75 here by symmetry. And lastly, 10, 10 is 1.5. So we can now compute these displacements, U4, U6, U8, U10, as the product of the inverse of this matrix and this force matrix here. Then the answers would be U4, which corresponds to theta B, U6 theta C, U8 theta D, U10 theta E, would be these values here over EI. And since EI is 100,000, so 1.508373 times 10 to the negative 3 radians. U6 or theta C, negative 7.917486 times 10 to the negative 4, and so on and so forth. So we have theta D and theta E also. Having found this, then we can now compute the member forces. And before that, let's solve for the displacements at A and at F. So considering AB, imagine that A is fixed and B is fixed. So since the load is acting at the fixed end, it will not produce moment. And the reaction here is upward, 15 kilonewtons, the fixed end force. Therefore, the nodal load is 15 downward. So that's why we have negative 15 here. No moment at A. Then let's just call the fixed end forces at B and C at B as F3 and F4, because we have found already the displacement at B, delta B 0 and delta 3 0, and delta 4 or U4 is theta B, which is this in terms of EI 150.834787 over EI. So 0 delta, sorry, 0, we have U1, U2, U3, which is 0, and U4, which is theta B. Then we copy the stiffness of AB. We'll just consider the upper half because the lower half is not important. Anyway, this is this 2 by 2 matrix times this matrix U1, U2 here, then plus this matrix times this 2 by 1 matrix here. So simplifying, we have negative 15, 0 equals this 2 by 2 matrix times U1, U2, then plus this 2 by 2 matrix times this 2 by 1 matrix. So let's expand. Negative 15 is equal to negative 1.8 times 0 plus 1.8 times 150.83743 over EI. So cancel EI because we have EI here. So therefore, this force value here becomes negative 15 minus 1.8 times 150.83743. And that would be negative 286.507. Then this value here becomes 0. So equals negative 1.8 times 0. So still 1. It's still 0. Then 1.2 times 150.83743. Therefore, the force value here becomes 0 minus 1.2 times 150.83743, and that's negative 181.005. Then equals EI times this matrix times U1, U2. So from here, U1, U2 can now be computed as the product of the inverse of this 2 by 2 matrix and this new force matrix. And the result would be U1 negative 335.007 over EI, and U2 175.837 over EI. Then for EF, so at E, we'll just call it F9, F10. Then let's consider EF as uniformly distributed load and fixed ended. This is here. So 24 kilonewton meter 1. So the moment here is 24 1 square over 12. So 2 counterclockwise. Then at the right 24 same 24 1 square over 12. So 2 clockwise. Then the fixed end reaction here is 24 times 1 over 2. So 12 upward, 12 upward. So at F, the nodal loads would be opposite to this. So we have downward 12, so negative 12. That's why you have negative 12 here. And since this is clockwise, the load should be counterclockwise. And the counterclockwise moment is positive 2. Then we grab the stiffness of EF, which is this, just the lower part, because the upper part is not important. Then expand, so negative 12, 2 is equal to this 2 by 2 matrix times this 2 by 1 matrix here. By the way, delta 9 is 0 because it is a support, and U10 is theta E 270.7496 over EI. Then you have U11, U12, which corresponds to delta F and theta F. So when we expand, so negative 12, 2 equals this 2 by 2 matrix times that, then this 2 by 2 matrix times this. So when we expand, negative 12 equals negative 18 times 0, then negative 9 times 270.7496 over EI. So we can cancel EI. So when we transpose, this becomes negative 12 because that's negative. So plus 9 times 270.7496. It becomes 2424.7464. Then 2, so equals 9 times 0, which is still 0, plus 3 times 270.7496. So therefore, 2 transpose 3 times 270.7496, so it becomes 2 minus 3 times 270.7496, and that's negative 810.2488. Then equals EI times this matrix times U11, U12. Then from here, we can now compute U11, U12 as the product of the inverse of this 2 by 2 matrix and this new force matrix. And the result would be U11, U12 equals 268.7496 over EI, and U12 268.083 over EI. So after that, we have the fixed end, the member forces. So shear AB, moment AB, shear BA, moment BA equals EI. This is the stiffness of AB. The corresponding displacements U1, U2, U3, U4. We have U1, U2 already computed there. Then plus the fixed end forces. So since this is considered fixed, no fixed end moments, so the fixed end force here is upward, which is equal to 15. So that's why you have 15. Moment, fixed end moment 0 at A, 0 also at B because the load is acting at the fixed end. Then 0 moment, it will not produce moment also. So that's why 0. So getting the product of this and this, the result would be shear AB is 0, of course. Moment AB is 0. Moment at A is 0, of course. Then shear BA 15 kilonewtons and moment BA negative 30 as expected, which is equal to MBC in the classical method. So that's why the moments would be entirely opposite for classical methods. 3 moment equation, slope deflection equation, moment distribution. than the results in matrix. So this is MBA, which is moment B, C, or moment B in the classical methods, but they are equal numerically. Next, for BC, we have shear BC, moment BC, shear CB. Shear CB, by the way, is the reaction just to the left of C, and we have moment CB, which is moment at C in the classical methods. Then this is the stiffness of BC. We just copy from here, and displacements delta 4, delta 30, U4. This is U30, U4, and U50 or delta C, then U6, which is theta C. Then fixed and forces, uh, 11.52 downward, so that's why we have negative 11.52. By the way, this 11.52 is obtained by summing up moments considering BC, summing moment about C equals 0, so it should be downward. So fixed force BC times 5 equals 76.8. Fixed end force BC plus 120 equals 76.8 plus 100.8. So 76.8 plus 100.8, then minus 120, then divided by 5. So that's why you get 11.52 downward. So you just consider BC, summation moment C. So fixed end force BC, which is expected downward, times 5 plus 120 equals 76.8 plus 100.8. So you get 11.52. And summation forces Y, this should also be 11.52 upward because there's no load downward, only the couple load. So they are numerically equal but opposite in directions. For CD, we expect upward reaction. So upward fixed and force CD, the calculation is not presented, but I just explained it here. So fixed and force BC times 6, then plus 50 times fixed and force CD times 6 equals 128.8 plus 56.8 plus the moment of the load 1/2 of 6 times 24 times 2. So you'll get 54.93 upward. Then summation forces Y equals 0. 54.933 plus fixed end force DC equals 1/2 of 6 times 24. You'll get 17.067 kilonewtons, also upward. And finally, in DE, summation moment about E equals 0. So we anticipate that the fixed end force DE is downward. So fixed end force DE downward, so its moment is counterclockwise. Then plus moment of the load 24 times 4 times 2 because it is also counterclockwise. Then equals 418 plus 482. You will get 177. Then summation forces Y equals 0. 177 downward plus 24 times 4 downward, then equals fixed end force ED. So 177 plus 24 times 4, you'll get 273 kilonewtons upward. And finally, at EF, EF, uh, this is it. So the fixed force E upward 12 and moment counterclockwise 2 at F upward 12 and clockwise 2. So we are already through with AB. Let's proceed to BC. Stiffness of BC, displacements, then fixed forces, negative 11.2. This is clockwise, so positive 76. This is clockwise, so negative 76.8 in matrix. Remember, clockwise is negative, counterclockwise is positive. Then at the right, we have 11.52 upward, so positive 11.52. Then clockwise 100.8, so negative 100.8. So the product of this and this plus the corresponding fixed forces will give us shear BC 9.119 kilonewtons, which is the same in the classical method, MBC, which is numerically equal to this, correct? Then shear CB negative 9.119 kilonewtons, MCB negative 104.406, which is the same as M sub C CD in classical method. So that's correct. Then for member forces of CD, we have shear CD, MCD, shear DC, MDC, stiffness of CD, then displacements U5, 0, U6, negative 79, you just look at there, U7, then U8. Then fixed forces, positive 54.933, this is counterclockwise, so positive 128.8. Then positive 17.067, then counterclockwise, so positive 56.8. So obtaining the product of this and this, then plus the corresponding fixed forces, you'll get the member forces of CD 55.932 kilonewtons, 104.406, which is numerically equal to that, 16.068 kilonewtons, which is supposedly RD left, which is the same in the classical method, and moment DC, which is moment DE, which is the same in the classical method also. Then we proceed to DE. DE, this one, stiffness of DE. Then this is U7, 0, U8, U9, 0, U10. Then fixed forces, negative 177. This is clockwise, so negative 418. This is upward 273, so positive 273. Then clockwise, so negative 482. Product of this and this plus corresponding fixed forces. So shear DE, fixed member forces of DE would be 23.203 kilonewtons. Moment TE, negative, the negative of this value. Then shear ED, then moment ED, which is moment at E. It's correct. And finally, for EF, member forces EF, stiffness of EF, then the displacements 0, the U10, 0, U9, 0, U10, theta E, 270.7496 over EI. This is U11, and this is U12. Then fixed forces, positive 12, positive 2 counterclockwise, positive 12, and this is clockwise 2, so negative 2. Obtaining the product and adding the corresponding fixed forces, you'll get 24 kilonewtons for shear moment EF, shear FE, which is expected 0, and moment FE 0. So that's it for this video. I hope that you were able to understand the explanations. Then if we compute for the reactions, RB, for example, is shear BA plus shear BC. Shear BA is 15 plus shear BC 9.116. 15 plus 9.119 rather is 24.119 kilonewtons, the same as in the classical methods. R sub C is shear CB plus shear CD. CB is negative 9.119, CD 55.92, adding, so you'll get 46.813 positive, so it is also upward. RD is shear DC plus shear DE. RD shear DC, which is 16.068 plus shear DE 23.203, adding 39.271 kilonewtons upward. Finally, RE is shear ED plus shear EF. Shear ED, shear ED, shear ED is shear ED. Where is shear ED? 72.797 plus shear EF 24, adding, so we have 96.797 kilonewtons apart. So that's it for this video. It's very lengthy, but that's really the solution.